Hello, this is Mr. Collier, and today we're going to be looking at the chi-squared test. So if we look at this, these three sets of data right here, we have a little table here for male and females and regular exercise or no regular exercise. So in the first case here, do males or females exercise more? So looking at the data, you have more males than females getting regular exercise, but there's also more males and females non-regular exercise. You can look at the differences here. There's 12 more males with regular exercise, and there's 20 more males with no regular exercise. But what does all this mean? And can we determine from this data if males or females exercise more? All right, and if we look at the second set of data, does getting a tattoo make you more likely to be infected with hepatitis C? Well, if you look at the data, it's kind of hard to determine. Looks like a lot more people who don't have tattoos don't have hepatitis C, but it's kind of hard to make sense of the data. And if we look at the third example here, does smoking marijuana increase your likelihood of becoming schizophrenic? Well, we have 58 smokers who are schizophrenic out of let's say about 350 or so if you add these two together. And out of the non-smokers, you seem to have a lot of non-smokers or non-schizophrenic. But we want to get a systematic method of whether or not there's a relationship or there's no relationship. Okay, basically, the first one we're trying to determine if the amount of exercise is dependent on your gender, or is it independent? So we're going to look at the chi-square test today to answer some of those questions. Okay, so the chi-square test for independence. In this test, what we're going to do is, now in this case, we have 400 randomly selected adults, and what we're going to do here is we're going to add up each row and each column and get those totals. So if I add these together here, I get 216. As we call this the observed frequencies. So these are the observed frequencies, and it's called a contingency table. But these are the observed frequencies in the contingency table. Alright, and what we're going to do is we're going to add up each of these totals here. So this is going to be 184. Here we're going to have 208. Here we're going to have 192. So those are totals for each row and column. I'm going to use that in a second in a calculation. So to calculate the chi-squared value, okay, this x symbol is actually the Greek symbol chi. So chi-squared, calculating chi-squared, we're going to get what we call the observed frequencies, which is what we have here. So these are the observed frequencies. We'll call that F0 or F0 for observed frequencies. And expected frequencies, FE. We're going to make another table now of expected frequencies. Okay, so that's what we're going to do next. To get the expected frequencies, we multiply the row sum by the column sum and divide by the total. The total number of people here is 400, so I multiply 208 by 216 to get this value. So we'll do that. So here we do 216 times 192 divided by 400, and here we'll do 184 times 192 divided by 400, and here we'll do 208 times 184 divided by 400. Okay, we're going to do all of that and get those values. So I'm going to do that on my calculator real quick. Okay, so what this expected frequency table shows us is what we expect to get if gender and exercise were totally independent. So if gender and exercise were not related at all, then these are the numbers we would get. So that's 112.32. So that's what you expect. That's how many males you expect in this group to do regular exercise. Okay, so if we look back at the observed frequencies, we actually had 110 males who have regular exercise, and the expected value is 112 males who have regular exercise. So it's not far off the expected value, so we can expect that probably there's no relationship between gender and regular exercise. So we're going to work out chi-squared and see what happens. So here's the chi-squared formula. And notice here that we have observed frequency minus expected frequency squared divided by the expected frequency, and you sum all those up. So what this actually, if you look at what kind of number this might produce, if the observed frequencies are very close to the expected frequencies, we'd get a very low chi value. So if it's a low chi-squared value, then the observed frequencies and expected frequencies are very close to one another, so they'd be independent. Okay, and a high chi-squared value would mean that the values are dependent. Alright, so if the variables are independent, the observed values will be similar, and this is what I was just saying, and the chi-squared will be small. If the variables are not independent, that's another way of saying dependent, okay, not independent, then there will be bigger. There will be a bigger difference between observed values and expected values, and the chi-squared will also be large. Okay, so this is how we work it out here. This is from my first table, my observed frequencies. And this is from my second table that we worked out, my expected frequencies. Okay, and here we subtract them, and these are the values we get, 106 minus 103.68. These are the values we get. And if we square these values, well, actually these are all the same, so we'll get the same number when we square them. And then we divide by the expected frequency. So we divide by this number in each case, and we get all of these numbers. Okay, and then you sum them up, and you get 0.2169. So that's what we did there. We subtracted the expected frequencies from observed frequencies. We squared those, we divided by the expected frequencies, and we summed them all up. After all that procedure, we get 0.2169. And that's called the chi-squared value, and it's very small. So that means that gender and regular exercise are independent. They are not related to each other. Okay, so we can't say that boys exercise more or girls exercise more because they're independent. Okay, so now let's take a look at how to do this on our calculator. So I'm going to show how to do that on our calculator. So let's go back to the original table. Alright, so the calculator can do all that work for us. So I'm going to enter basically a 2x2 table, right? So on the calculator, we're going to go to second function, and we're going to get a matrix, and that will be able to give us a 2x2 matrix, which looks like a table. So if I go to matrix and I go over to edit, I will click enter, and I can edit the matrix. This is a 2x2 table, so I'm going to put in 2x2. And there we go, we have a 2x2 matrix here. And we can enter these values, 110, 106, oops, I made a mistake here, hang on, 110, enter, 106, enter, 98, enter, 86, enter. So I've got all my values in there. And then we go to, let me just quit out of that mode. Then we can go to stats, go over to tests. We have lots of different tests here, t-tests, z-tests, 2 sample tests, whatever. We're not going to use any of those. We're going to scroll down until we get to the chi-squared test. So there's the chi-squared test. It's down at C, so we could have pressed alpha C to get to there. So chi-squared test, and we're going to, now this is our observed data. Alright, so that's in matrix A, that's where we put it. It will automatically produce your expected values in matrix B. So we just need to go down to calculate now. So click on calculate, and there it gives you a few pieces of data that we're going to look at later, but it gives you your chi-squared value, which is 0.217, which is very close to what we calculated by hand. Okay, let's take a look at the next example then. So here we're looking at a relationship between hepatitis C and getting a tattoo. So this is remember this is a contingency table with the the observed values. And we have, for total number of people with tattoos, we have 25 and 88, so that's 113 in total. And across here we're going to have 22 plus 491. We get 500 and 513. And the total number of people with hepatitis C in this study are 47. And with no hepatitis C, we have 579. Okay, so those are our totals, and we use that to work out the expected value. Let me show you how to do that with the calculator. We could do that with these values right here. We could multiply 113 by 47 and then divide it by the total. The total number of people, now this should add up to the same number as this right here, so the total is actually 626. Let's show how to do that on the calculator as well. So I have a second function matrix, and this is a 2x2 matrix. I go over to edit. Oops, go to edit. I'm going to put this in A. So I have 25, 88, 22, and 491. Those are my observed values. And the calculator will calculate the expected values for me if I go into the chi-squared test. So I go over to tests. Now I think chi-squared was at C. If I scroll down, it goes all the way down past 10 and goes to C. So I'm going to just press alpha C and see if it pops up. There it does. So this chi-squared test is here. It'll take those observed values in matrix A, and it'll put them in, put the expected values in matrix B, which is what I want. I'm going to click on calculate, and alright, so there's your chi-squared value is 42.4. So we're going to work that out in a second, but I also want my expected value table. Okay, so my expected values, I can actually, remember I went to B, so I can go to matrix, so second function matrix. I can go down to B and just click enter, and it gives me my expected values. So I'm going to actually just, so that's 8.48 for the first one. So 8.48. And for the one below that is 38.5. And let's check over, let's scroll over and see the rest. So 104.5, that rounds up to 105. And the next one is 474. 474. Okay. So those are my expected values. Now at this point I should probably tell you that you shouldn't use the chi-square test, or the chi-square test is not valid if any of these numbers are 5 or below. So they're all above 5, so that's pretty good. Now we got the expected value table. We're going to look at this here below. We're going to fill in the missing values. So we have in this column the observed frequencies. We're missing one. The one we're missing is 22. Okay. And the one we're missing for expected value is the one that corresponds to 88. So 88 is here. We're missing 105 in the other one. Okay. And we're going to subtract these values, so you can subtract them. Here you get negative 17 Here we're going to get positive number 491 minus that number gives us 17. Alright, and then we square all these numbers and then divide them by the expected frequency and so forth. You could finish that one by hand. And the chi-square statistics, we'll get that by summing this together. Let's just go ahead and finish that up then. So negative 17 squared is the same thing as 17 squared. That gives us 289. And over here, we're going to do 272.25 divided by the expected frequency, which is 38.5. Okay, so 272.25 divided by 38.5 gives us 7.07. So that's about 7.07. Now we add all these up, get the total, and that's actually equal to your chi-squared statistic. So we're going to add that number to 0.6097 and 2.75 and 32.2. I get 42.6. 42.6, which is actually a pretty high number. We'll talk more about what that means later, but that basically means that there is a relationship here that they are dependent, or they're not independent, which means they're dependent. That means that people who get tattoos are much more likely to have hepatitis C than people who don't have tattoos. Okay, so let's take a look at another example here. Alright, now, null and alternative hypothesis. So in this case, we're looking at whether or not smoking marijuana is related to schizophrenia. Okay, so are those two things dependent or independent? So we have two cases. We have what's called a null hypothesis and then the alternative hypothesis. Okay, so there's only two possibilities. Either these two are dependent or they're independent. Okay, so the null hypothesis is always that they're independent. So smoking, so in this case your null hypothesis is smoking marijuana and schizophrenia. I'm just going to abbreviate here. Schizophrenia are independent. So null hypothesis is always that there is no relationship there, that they're independent. And your alternative hypothesis is that smoking marijuana and having schizophrenia are not independent. Okay, which basically means they are dependent and there is a relationship there. Alright, so if we look at the next table here, these are expected values. So you always have the observed values and then you have to work out the expected values. Okay, we can get the, remember you have to get the total of the columns and total of the rows and stuff like that, or we can just use our calculator, which is what I'm going to do right now. So I'm going to go to second function, matrix, and I'm going to go over to edit and enter. We get a 2 by 2 table, and then I enter these values. So 58, 73, 269, and 624. So those are my observed values. I can go now into stat tests, and it's under alpha C, so I'm going to click on that, and then we have the chi-square test. It'll calculate those observed values I just typed in and give me expected values. So I'm going to do that. I'm going to calculate, and we have chi-squared is 10.5, so I'm going to write that down real quick. Alright, So we're skipping this part by hand. So we have 10.5 is the chi-square statistic. And if you want to get the expected values, you can go to second function matrix, and they're in matrix B, and enter. So 41.8, 41.8, we have 285. Alright, we have over here 89.2 and 608 if I round up, 608. So those are the expected values. We expect in the data set this size to get 608 here for the non-smokers without schizophrenia, but we have 624, more than we expect, right? Here we expect 41.8 smokers of marijuana to be schizophrenic, but there's actually 58. So that suggests maybe they're dependent. And the chi-square test verifies that. It's 10.5, which is a high number, so that means that they are, well, they're not. So that means we have to reject the null hypothesis and accept the alternate hypothesis that smoking marijuana and schizophrenia are not independent. They are dependent, right? So we could have done all this by hand. Just type in the expected values here, which is 41.8, and subtract them, and then square them, and then divide them by the expected value again. Add all those up, and you add all of those up in this column, you should get about 10.5 as well.